Hello everyone, today we will discuss about UV visible diffuse reflectance spectroscopy and its application towards photocatalysis, right. So, we will start from the last word, spectroscopy. What is spectroscopy? You must have some idea on it.
Interaction of matter with light.
Light, right. Okay. Spectroscopy is the study of interaction, right, of light with matter. If light will interact with matter, then what will occur?
Transition, electronic transition.
Okay, what is photoelectron effect? You first tell me.
Light incident upon a metal surface, then electron ejected.
Right. Photoelectron effect means when light irradiate on the surface of a metal, that will eject a electron. Yes or no? This is photoelectron effect, na? Okay. So, this interaction of light with matter is known as spectroscopy. So, we have this basic idea what is spectroscopy. Then second one is diffuse reflectance. What is diffuse reflectance and what is UV visible? We will discuss it, right. Then what is the importance of UV visible diffuse reflectance spectroscopy? It is shortly known as UV visible DRS, right. UV visible, it is DRS, diffuse reflectance spectroscopy, okay. And what is its application towards photocatalysis, right. What is its application towards photocatalysis, right. It is spectroscopy. Spectroscopy is the study of matter using electromagnetic radiation. That means it is the interaction between matter and photon, right. Photon means light, na. It is the interaction between photon and matter, okay. Then what will occur? You just see here. Suppose it is your sample holder, right, and this reddish color means this is your sample, okay, and it is your incident ray, it is your diffracted ray, right. Suppose it is another example. Suppose this one is your sample holder and this yellow color is your sample, okay. This is incident ray, right. Then what will occur? The light may transmitted, reflected, refracted, okay. So, when the light just interact with matter, then what will occur? It may reflected, it may transmitted, it may refracted, it may diffracted, right. And on the basis of the reflection, refraction and diffraction transmission, we will get various information of the matter, right or not. We will get some information from diffraction, we will get some information from reflected ray, some information from transmitted ray, some information from refracted ray, like this, okay. This is the interaction of matter and light, clear. Now, come to second slide. It is types of spectroscopy, right. When matter interact with light, what I have told in the previous slide, when light interact with matter, we know it may reflected, it may refracted. On the basis of that, it is categorized into three types, right. It is categorized into three types. First one is absorption spectroscopy, okay. Second one is emission spectroscopy, and third one is fluorescence spectroscopy or emission spectroscopy. Emission, absorption, emission and fluorescence spectroscopy, right. And some examples are infrared spectroscopy means IR. IR is an example of atomic means absorption spectroscopy, and UV visible DRS is an example of absorption spectroscopy. Here NMR, you know NMR, nuclear magnetic resonance, this type of experiment is an example of emission spectroscopy. This type of analysis technique, it is not experiment, it is analysis technique, analysis technique of the sample. And Raman spectroscopy and X-ray spectroscopy are an example of fluorescence spectroscopy, okay. And today we will discuss about ultraviolet visible UV visible DRS, which is an example of absorption spectroscopy, okay. So, the first question arises here, why it is called as absorption spectroscopy, right.
Light get absorbed, or this phenomenon is only it can be explained when the light is incidented or when the light is absorbed.
right. Actually, in this spectroscopy, we just predict the nature of a metal or any type of sample on the basis of absorption of photon. Okay, how much photon it have absorbed. Suppose you just take an example. Suppose it is sample holder, right, and it is you just irradiate photon from this side. Okay, suppose it is 100%. Incident ray is 100%. Okay, and this sample holder contains some sample. Some ray will be transmitted in the opposite side, and that ray, the efficiency of the transmitted ray is must not be 100% if it is not a transparent sample. If it is transparent, for example water, still it have some less efficiency. Okay, so how can we calculate what is the absorption, means how much energy have been absorbed by the sample? 100, it is 100, I0, it is transmitted ray, suppose it is 87. So 100 minus 87 is 13. So on the basis of that, we can get how much energy has been absorbed by the sample, and the absorption capacity coefficient is different for different material. Yes or no? If I will take ethanol, methanol, for example water, right? Okay. Different methods of spectroscopy may be employed depending on type of sample, and analysis need to be studied qualitative as well as quantitative property. Means by this instrumental techniques, we can calculate the qualitative property as well as quantitative property. In some cases we can calculate the quality, what is the quality, means what is the nature of the sample. In some cases we can calculate the quantity property. What example I have previously told you. Okay, suppose you just take an example of NaCl solution. You just take an example, first example, only water, right? We just irradiate a light source on the sample. Okay, suppose 100% light will be transmitted, for example. Now what we will take? We will take suppose sodium chloride solution, 5% sodium chloride. Okay, now that sodium chloride will absorb some light. Okay, and the reflected or the transmitted ray will be suppose 90%. If we will increase the concentration of the solute, okay, simultaneously the absorption capacity will also enhanced. Means absorption capacity depends upon the concentration of the solute. Yes or no? Right. So by this technique we can calculate the qualitative as well as quantitative property. This one is the example of quantitative. How much quantity of solute is present in the solution? This is a quantity. This is a quantitative measurement, right? Now come to next slide. Ultraviolet UV visual spectroscopy is used to analyze the target sample by measuring visible and ultraviolet light emission. Okay, I have already told you absorption, emission. Okay, on the basis of how much light it emits, we can calculate how much light it absorbs. Yes or no? The emission in the visible light of the electromagnetic spectrum affects color of the compound. Yes or no? Suppose we will take different color of compound. One is suppose zinc oxide, it is white. Okay, it will reflect 100% light. Yes or no? If we will take suppose graphene, it is graphite, RGO, suppose a black color material. So you know black will absorb maximum light. Yes or no? So that the reflection or the emission of light depends upon the color of material. Yes or no? It is highly dependent on the color of material, right? This method is based on the principle that the range of the electromagnetic spectrum measures transition in the state of the electronic in the compound. Molecule of the target compound absorb energy emitted by the spectrometer, which moves their electrons to a higher orbital. Okay, we will discuss this in the next slides. Okay, you know it tells about when a compound or a sample absorbs light, what will occur? Two things will occur. Okay, if the photon energy is sufficient to excite electron, then it will excite the electron, the transition will occur. If the light source is not sufficient, what will occur? The electron will not be excited. The energy will be lost, dissipated in the form of heat energy. Yes or no? If it is not sufficient to excite the electron, then the light energy will convert to heat energy. Right? Okay, this type of actually UV visual spectroscopy have a wide range of application. Okay, but Basically, this type of analysis is most commonly used for biological macromolecules and inorganic compounds in a liquid solution, right. Now, we will move to next slide. Okay, this is a very fundamental slide. Okay, you know, this is the range, means different wavelength of light, right. You know, there are 7, 1, 2, 3, 4, 5, 6, 7, 8 radio wave, microwave, infrared, visible, near UV, X-ray and gamma ray. Yes or no? 7 types: UV, visible, infrared, microwave, radio wave. This type of wavelength means what? Different wavelength of light spectrum just shown here, right. And today we are discussing about this visible and UV light. Okay, you know what is the role of this UV and visible light? This range of light can excite the electron of atom. Okay, you know, here I have written radio wave can cause nuclear spin transition. Nuclear spin, you know, +1/2, -1/2 in NMR. You have idea, na? In cell, 2 electrons are there. One is plus half, minus half, like that. So in radio wave have sufficient energy that it can alter the spin of the nucleus. Got it? Radio frequency have such much energy that it can alter the spin of the nucleus. Microwave can cause rotational motion, you know, vibrational motion, rotational motion, translational motion, right. So microwave can cause rotational motion of the molecule. Infrared IR, it can cause molecular vibration. And here visible and UV and visible, okay, it can cause your electronic transition. In this range, the electronic transition can occur. It have not much energy that it can alter the spin of the nucleus. It can vibrate the molecule. It have not such much energy, but it can, what can it do? It can excite the electron. Okay. And you know, X-ray, gamma ray, this can cause, it have much energy that it can ionize. Okay, it can ionize. Okay, got it. So today we are discussing about visible and UV visible light source, which can cause electronic transition in the molecules, right. And here I have shown here, you know, pi bond, pi star bond, sigma bond, sigma star, pi star and n. Okay, these are what? Bondings. These are anti-bondings. Okay, and you know, sigma to sigma star transition can occur in alkanes. Yes or no? Right? And pi to pi star transition can occur in unsaturated compounds which have double or triple bonds. Alkanes have only single bond, so only sigma to sigma star transition is possible there, right. The compounds which contains means heteroatoms, oxygen, nitrogen, sulfur, like these atoms, their n to pi star transition will occur. Okay, n to sigma star transition will occur. And if the compound contains carbonyl groups, C double bond O, at that case n to pi star transition will occur. Okay. Yes. What is it?
Pi star, pi to sigma to pi star double.
N to pi star and n to sigma to sigma star, sigma to pi star, then
N to pi star double like
carbonyls, both are possible there. Sigma to pi star and n to pi star, both are possible because that contains double bond as well as heteroatom. Yes or no? That contains double bond as well as heteroatom. So both are possible there, right? Okay, what we have discussed till now, that was about spectroscopy, some idea, light to matter interaction, and their consequences. What happens there? Okay. Now, it is a very technical term, diffuse reflection. What is diffuse reflection? We know what is reflection. Okay. If we keep a mirror here, okay, and when an incident light strikes the mirror, what will happen? Reflection will occur. Okay. Then what is the difference between reflection and diffuse reflectance? Diffuse reflection.
Maybe there will be some obstacles.
Not obstacles, not exactly that. Actually, you know, here we are using UV visible spectroscopy for sample analysis. Okay. Suppose what will you do? We will take a suppose chalk. We will take a chalk and grind it. Right. We will take a chalk and grind it. In the powder form, it is not means when we put it in the on the surface of sample holder. It have different planes. Okay. So, when we arrange it, put it on the sample holder, all the planes may not be arranged in the same sequence. Yes or no? Just like this, you just see here, it have different planes. We have arranged here and it have different planes. So, when light strikes here, it moves there. When light strikes here, it moves there and again comes in this direction. Right or not? If we will take a very plain surface, a iron piece or a mirror piece, it will strike and move in one direction. That is reflection. If we will take a powder, that are different planes having different angles in different direction, like this. Okay, like this. So, in this case, multiple reflection will occur. Okay, in this case, multiple reflection will occur when the incident light strikes the sample. This is called as diffuse reflectance. Got it?
In sample, in mirror, there can be reflection. In sample, how it get reflected?
Sample? You know, okay. What you are telling, you know, you can take anything, 100% light cannot be absorbed and 100% light cannot be reflected. Right? In mirror, if 90% or 95% reflection occurs, here 10 to 15% reflection will occur, but reflection will occur.
Okay, so the material is like that can reflect.
Reflected. Yes.
Some of materials may be there, it cannot reflect.
That is okay. What you are telling about black body, you know.
No.
You know, in physics there is a term black body. Black body, which is practically there is, we know, a complete pure black body means is not possible in, okay, to create it is not possible to create a 100% or ideal black body which can absorb 100% light. If we can create a ideal black body, there is no reflection percentage 0%, but that is completely ideal. We cannot make a 100% ideal body which can absorb 100% and chance of reflection is 0%. So, any substance we can take, okay, that must reflect some light whether it is 0.01%, it might be 0.001%, but definitely it will reflect some light if it is not a ideal black body. So, in this case that will happen. Got it? Okay. So, what is diffuse reflectance? Clear? So, why it is called UV visible diffuse reflectance spectroscopy? Why it is not called UV visible reflectance? Because we are using a sample which is in the powder form. Okay. Got it?
We are using visible light or UV and visible?
We are using UV light as well as visible light. Two lamps are there. I will explain that.
Okay.
Okay. In next slides, I will explain that. Okay. In the lamp here, you know, this is the UV visible lamp, our spectrometer. In this spectrometer, UV lamp is present as well as visible lamp is also present.
Visible lamp is this the light we are observing.
I will tell you in the next slide. Okay. Understand? Clear or I have in doubt? बुझ पार्छ त? Clear? Okay. Instrumentation. So, that was all about your spectroscopy, that was all about your that is what? Diffuse reflectance. So, diffuse reflectance spectroscopy is clear, diffuse reflectance clear, spectroscopy is clear. We have already discussed about UV visible, that is clear. So, then so what is UV visible diffuse reflectance spectroscopy? We have now some idea. Okay. Now we will come to the instrumentation, because without instrumentation we cannot do anything. Instrumentation is also important, right? So if you have any doubt, you can ask. No doubt.
Solid sample by DRS.
By UV visible DRS we can analyze solid sample as well as liquid sample. For solid sample, I have already told you. I am telling you. Suppose if we will take liquid, I have already told you, we can do qualitative as well as quantitative measurement. Okay, we can do qualitative as well as quantitative measurement. For liquid sample, we will do quantitative measurement. How much quantity is present, solid present in the solution, it is quantitative. For solid sample, we can do quality measurement. What is the band gap? Here the instrument we have only two sample holder. One is for liquid sample, one is for solid sample. Right? What is your question for semi-solid? In case of semi-solid, you know, then in semi-solid, for example, you just tell me what type of example you want to tell. You want to ask? Yes. For example, you just tell me one example, then I will explain. Okay. As a prior means basic fundamental, you just know. We will discuss that later, right? As a basic fundamental, you just know UV visible spectroscopy can be used for solid sample for quality measurement, for liquid sample for quantitative measurement. Clear? Okay. This is about our instrumentation, right? Commercial UV visible spectrometers are widely available in both transmission and diffuse reflectance configuration. Okay. In the instrument, in this UV visible DRS instrument, we have a chamber which can collect the diffuse reflectance light. Okay. We have the chamber which can collect and analyze the diffuse reflectance light. Okay. So that is why it is called as, this instrument is called as UV visible DRS. Okay. These machines often offer an extremely wide wavelength window over which measurements can be performed, extending from UV to near infrared regions. Okay. So these are some setups that is having in the UV visible DRS spectroscopy. What is light source? It is very important. Okay, light source is very important. Monochromator. What is the role of monochromator? We will discuss. Right. Long pass filter, transmission cell, diffuse reflectance sphere. It is a main hero. Diffuse reflectance sphere. It will collect the diffuse reflectance spectroscopy, means light. Various focusing lenses and optical fibers. Right. Items of notes are the type of light sources and long pass filter. The light source can come in the form of arc lamp, mercury, tungsten, halogen or xenon or tunable dye lasers. Okay, we will discuss which type of light source are used for which region. Which light source is used for UV source, which light source is used as a visible light source. Clear? Or have any doubt? You can ask. If you have any doubt, you can ask.
Diffuse reflectance sphere.
Sphere, yes, where? Here. Yes.
Sphere means it will be spherical.
No. It is just like a chamber by through which all the reflection can be collected. Means suppose you just assume a spherical body that have one hole. Okay, sample is there. It will strike the sample. You know, I have already told you, in different direction light will be reflected. So if the body, if you just take a 2D slide, then it cannot collect all the reflections. So it is just like a spherical, means around 70 to 80% half sphere or more than that, so that it can collect all the transmission lights, all the reflection lights that come, means causes in different directions, happens in different directions, right. So it just like, means it is just like as a half sphere or more than half sphere, just like that. So reflection will occur in all the directions, it can collect everything. Clear na? From? No. Here in UV visible spectroscopy, we just calculate from the the amount of light absorbed. Okay. So we can, what can you do? We can minus the the incident light, the intensity is 100%, the reflected light intensity, by just subtract there we can get how much light is absorbed. Okay, and that absorption causes what? Electron transition. So that is very important. Clear or in doubt? Okay. Okay, for liquid sample, this one is very important. Okay, here I have shown you two types of examples. It is the simple one. Okay, this is the lamp. This is the lamp. Here I have just shown for the cuvette. Anyway, this is the lamp. This is a light source. This contains different wavelength of light. Different wavelength of light. Then what monochromator will do? Monochromator, there is a prism test. When the visible light just pass through the prism, it separated into 7 colors. Okay, just monochromator do this here. It separates different wavelengths of light. Okay, this is the role of monochromator. It is very important. Clear? What is the role of monochromator? It will separate the different wavelength of light. This one is slit. It will allow only one type of wavelength at a certain time.
Okay, one type of
Wavelength.
at a particular time.
Particular means throughout the reaction, means throughout the experiment.
Okay, that means the slit will choose one of the wavelength.
No, the slit cannot choose. The slit have a very pinhole. What we will do? We will take a torch. Okay, we will take a black paper and do a pinhole. Okay, when we light the torch, what will happen? A very narrow light will pass through the paper and that will strike the sample. Our target is a narrow beam of light should strike the sample. So slit cannot choose. Slit will allow a very narrow.
My question is
Monochromator is used, right?
That means maybe it will choose only one type of wavelength.
I am telling that one. In UV visible spectroscopy, we are taking UV light source as well as visible light source. Okay, so that's why here we are using that here. Okay.
So I was confused that like red wavelength, green and blue wavelength are there. So out of these three, only blue wavelength of light.
No, not exactly like that. No, not exactly. In practically, what happens really? Okay, we are taking sample. Okay, and both means our UV light source and visible light source suppose are present, means are on. We do it in that range 200 to 800 nanometer. That is the UV visible light range 200 to 800 nanometer. Okay, the sample absorbs that light. If the sample is completely white, so at that case light absorption will be minimum. I have told you. It have a red color, green color, blue color, black color. The light absorption is maximum. Suppose ZNO, it is completely white in nature. Yes or no? So at that case we will get the band gap that is above 3 electron volt, because that is UV active. If the sample is completely white, that is UV active.
It depends upon the sample
Color. Yes.
which light it will absorb.
No.
Either UV or visible.
No, yes, right. Whether if the sample is completely black, it can absorb maximum color. If the sample is completely white, it will reflect maximum color, and the band gap will come around even 2.8, 2.9 or 3, or it may be above than that.
So from this spectroscopy we can also know the band gap.
Yes, sure. That's why we are performing this type of experimental characterization techniques here to get the band gap. I have told you what I told, qualitative as well as quantitative. Qualitative means to get the band gap of the material. Okay, Roshan, you know what you ask here. This slit cannot choose which color I will pass. It will pass only means a very narrow light source. Okay, means the diffract means the bunch of light will not strike the means slit means the sample. Okay, this this monochromator will just means separate the different wavelength of light, right, and this slit, it is slit, it will allow only a very narrow beam of light to pass through it. It cannot choose that which light I will pass, UV light I will pass or visible light will pass, no. Nice question. If we will not use monochromator, you know, if when a single light source will strike here, okay, you are able to see here, yes or no, you are able to see here at which point it strikes. If we will use a torch completely, it will give a maximum diffraction, reflection. You just think the practical sense. If I will give a very narrow light, incident light, the reflection, refraction, it will be completely clear. What is the intensity of incident light, okay, and what is how much amount is reflected, refracted. But if you use a bunch of light there, we may not get the same result as we are getting here. In various physics experiments, you can get this one, monochromator and slit. Double slit experiment you may have in physics, there is some experiments, right. So, slits are used only to allow a very narrow source of light to strike the sample, clear. This is the importance of monochromator and slit, clear. So, actually slit, you know, slit cannot choose which light I will pass, to which I will oppose, no. It will, what example I told you, I will take a plain paper or black paper and do a very small hole. Now just light a torch, only a very narrow light source will go there and the next light, and that will, suppose if a sample is there, it will strike that, clear.
Then what is the use of monochromator?
Sorry?
What is the use of monochromator?
What is the use of monochromator? What I have told you? Okay, your question is if it separates it in different colors, but actually slit means allow every colors, means it not separates whether it is blue color, it is green color, it is yellow color, right.
Then what is the use of monochromator?
Okay, we will discuss that later, I think. Actually what I know about this monochromator and slit, I know this thing. If this question arises, I will think about it, okay. Then what is your, if actually this question is important, actually if it separates in various colors and slit is not able to means choose which color I will do pass, a slit only do one thing, that will narrow, means that will yes, like that, okay. Polychromatic, monochromatic, actually it will allow it will allow a monochromatic light source. Yes. Fixed, no. Okay. Or second chance is there, what you are asking, it might happen, okay, that if it means what I told you, that the light absorbed depends upon the color of the sample, okay. Suppose I will take a black color sample, I will take a red color sample, I will take a yellow color sample. So, same light source will not strike that one, okay. What you are asking, it might, that is different thing. Give you what you are telling, that is different. White light it will absorb, the complementary color it will show, that is different thing. So, actually what Roshan asked, that is if it just separate different waveforms of light, then what, and slit cannot means decide which type of light I will pass through, then what is the role of monochromator? We just taken one example, right. We will take 3 to 4 samples, one is white, one is black, one is yellow, one is red and one is green, 5 example. So, and the wavelength by which they will be excited will not be same, right. So, slit, by slit, you know, when by through slit different wavelength are passed to the sample, by only one wavelength of light, that will be get excited, it might be happen. Roshan, yes or no? What do you think? Suppose when blue color light will pass to the slit, that sample may not be excited, but when green color light will,
In the moving condition.
yes, yes, okay. So when different a wavelength of light will pass through that one, that may cause the excitation of the electrons of the sample. Right? No, no, समझे नहीं? अच्छा, हाँ, it is possible. Okay, it is possible. You know, we are able to change the wavelength of light by changing the slit. By changing the slit, we can change the wavelength, means a particular wavelength of light that will strike the sample. Suppose we need 200 to 500 nanometer. Okay, we just put that at that range, the slit will automatically change. That portion of light, that energy of light will pass through that. We can manually change it, and it is possible to slide that one. Ritik, am I clear? Okay, clear. So I think the monochromator and slit is now it is clear. And what Roshan asked, that is very important question. I think that one is right, that after the separation of different wavelengths of light, the slit just allow each wavelength of light one upon another, okay, and at a particular wavelength a sample means the transition occurs, right. So it is single beam, okay, and this one is important in our UV visual spectrophotometer that have this type of instrumentation techniques, you know. Then what is this one? You know, this is our lamp, this is our monochromator. I have already told you what is the role of it, and this is a slit. Suppose at this time, suppose blue color light pass through the slit, and here two mirrors are there. It is rotating mirror, okay. Only for liquid sample. It is quantitative measurement, quantitative, right? And this is a reference. A reference means solvent. A reference means only solvent. And this is a sample, solute present in the solvent, right? So you know this is I0, because I will get 100% light here, and here IT, transmitted light I will get here, because some light will be observed here. So after observance, transmission light I will be get here. So what will I do? Now I will compare what is the value of I0. Suppose total mark is 100, okay, I have secured 95%, suppose 95, right. So how much energy get absorbed? 5, like that. So this is the transmission, right? This is the 100% light. So from this variation we can calculate how much amount of solute is present in the solution. Then what is the concentration of solution? This is a rotating mirror. Rotating mirror. Sometimes it passes this one, and while the position is like this, it reflects the light in this direction and it moves in this direction. This is a rotating mirror, right? And for such, this is known as cuvette. What? Cuvette. Here I have written cuvette, right? Cuvette may be glass or plastic. If we will study only for visible light source, visible type of sample, it may be quartz. We have the quartz cuvette. It is very costly. It can be used for both visible as well as UV type of material. Acrylic, but acrylic type of cuvette also used for the same purpose like as quartz cuvette, but here we have only quartz cuvette, which have both visible light, which can be used for both visible as well as UV type of material in both the light source. Clear? Or have any doubt?
Okay, that means we are using here split dual beam.
Yes, yes, it is dual beam.
Okay. Single beam UV is not required, right?
There is
In single, keep in mind one thing, what I am telling. Here there is a reference by comparing with which we can get the result very accurately. Accuracy is very much important in each analysis and experiment. Yes or no?
Yes.
So you just tell me, in comparison between these two, in which method we will get the accurate result?
Obviously split dual beam.
Clear. So we have this one, this experiment. Okay. and this is used to get the quantitative. I am telling the next slide I will go to that. Yes, there is also reference, I will tell you, right. So this is for the liquid sample. By this process we can calculate the quantitative measurement, means how much solute. You know what I have already given you an example. If I will increase the concentration of solute, then it will absorb more light. Suppose I will take 1 drop of ink in water, then I will put 2 drops ink, 5 drop ink, 10 drop ink. So when concentration increases, light absorbance also simultaneously increases, right or not? Yes. So on that basis we can calculate what is the concentration of our solution. Clear? It is a quantity measurement. Clear? We will move to next slide, or have a doubt? Okay, clear? Absorbance and the Beer-Lambert law. You know what is Beer-Lambert law, and this type of concentration calculation just follows this type of law. We all have that knowledge. What is Beer-Lambert's law? Okay. That is absorbance equal to epsilon C L. L is the path length, C is the concentration. Okay.
Path length of that
cuvette. Path length of the cuvette in which we have taken a sample. And C is the concentration, right?
Molar extinction coefficient.
Yes.
That we have to calculate.
We have to calculate
For that
sample, because it sorry, epsilon molar extinction coefficient is different for different samples. So we have to calculate during the reaction. Okay, it is different for, yes, what is the problem?
I think epsilon's value is like K by 2.003 or something like that.
Epsilon is constant, you are telling? Dependent.
I'm talking about the K value. Depends on the K. I think.
Oh, what is K?
Rate of the reaction, rate constant. I think I'm not sure.
Okay. So this is the basic formula, Roshan.
Yes.
You know what is K here?
K.
We just actually epsilon, we just put epsilon as a constant here. What we are telling, the value might be that K by something, that we just take here as epsilon. You are telling that one, no? Okay. Just epsilon here the absorption constant, right? Epsilon is the molar extinction coefficient. It is a constant for the absorbing species and defines the absorption of the species at a particular wavelength. It is determined by the number and types of chromophores present in each molecule and absorption species. So it will come, what? Epsilon value will become different for different type of what? Solution or anything. Sample. Clear? So you know this type of means quantity measurement or concentration calculation basically follows this type of rules, and still it have some what limitations, and we will not discuss it here. For the timing it is not equal for us. Okay. Clear or haven't doubt? Here A is observance na? Yes. During the during our experiment, I will tell that to you how to calculate epsilon there. I have not provide that everything here. During reaction, when we will do our quantity measurement of any type of material, I will explain that there. How can we do calculate epsilon there, and after that epsilon calculation, yes, and after that calculation, that epsilon will be constant for the related experiments. Suppose we will do for different type of concentrations, 20 ppm, 40 ppm, 100, 50 ppm. Okay. So first we will get what is the epsilon value from the UV visible spectrophotometer, right? And by putting that value, epsilon value, we will get how much concentration of the substance present in the solution. Get it? We will directly get from the what is the our epsilon value from UV visible DRS spectroscopy for the parent material, because epsilon we will calculate epsilon value for the parent material.
Then for different concentration it will remain
it will remain constant. Suppose I will take 100 ppm solution, so I will get epsilon value from that one. After some treatment, that will be reduced or that may be decreased. So to get how much concentration has been degraded, at that case I will put the same epsilon value to get the value different concentration of the sample. No, that is fixed. That is fixed. The instrumentation setup is already fixed. We cannot change that. Light. AL is a path length of the cuvette. 1 centimeter, 1 centimeter square, 1. Length of the L is the our path length, you know. Okay, L is the path length of the cuvette, 1 centimeter square, through which it will pass through. Through which, you know, in the cuvette 1 centimeter square is there, 1 centimeter, 1 centimeter. It is a okay. When light pass through 1 centimeter square, it is a path length. Clear or haven't doubt? Roshan? Clear or haven't doubt? How do you know? Acha, you have some experience. Okay, we just put the means the, you know, once you know, in cuvette it is 4 sides. 2 sides are completely transparent and 2 sides are slightly hazy. We have to put the transparent side to the light source. Okay, if we will put the hazy side, we will not get the right result. Okay, if this part is transparent, the opposite part is also transparent. If this part is hazy, this part is hazy, and we have to put the sample order like this. Light source will pass from this side. Clear or haven't doubt or any doubt? No. Right, scatter, right. Out of plane, that is right. Because the internal reflection will occur there, na? That will inhibit that. Yes or no? That will inhibit the internal reflections. That will pass only in one direction. That helps for that purpose. Clear? Clear or have any other doubt? Okay. Okay, for solid sample. Okay, it is our qualitative measurement. Qualitative measurement. Okay. So we have already told you up to this one. Okay, here slit is not present. We are not using slit. Okay, because in solid sample, you know, we are providing all the source of light. All the source of light. Rotating beam, split mirror, rotating beam. It is a rotating beam. Okay, this is okay. You have asked me what is the reference in solid case. What is the reference? You have asked me, na? Barium sulfate. No, it is solid. For solid, barium sulfate is the reference. That has been standardized on the basis of barium sulfate. Have you know anything else? If you know, you can share. That might be. I don't know exactly what is the reason, but it has been used. Sorry, that is not transparent at all. That is like your chalk. Chalk is not transparent. Chalk is transparent. So barium sulfate is just like that, and it is used for that purpose. Means as the reference. Okay, for solid sample characterization, we use barium sulfate. We have to first do standardize by using barium sulfate, using as reference. Then we will do analysis of any sample. We can do, right. So same principle happens here. It is a rotating mirror. It is a sample, and it is a reference. So this is a detector. What I have told you, sample, one is a reference, detector detects both the light, then it can calculate which type of, what is the concentration or which type of graph that will show. Okay. So in solid sample analysis, we can get a graph. What? Graph directly in instrumentation, instrument. it will convert the data into a graph. But in liquid sample analysis, we will get some only value of concentration 0.056 or 0.089. Then after we have to do calculate manually. At that case, we will not get any graph. And so that here we have shown here only as graph type structure. Right. Okay, you know, I have told you two types of lamps are basically used there. One is deuterium lamp, one is tungsten filament. It is used as visible and near IR source, and deuterium lamp is used as UV light source. So both the light sources are present in our or any type of UV visible DRS spectrophotometer. Okay, it is very important. Deuterium lamp and tungsten lamp.
We are using deuterium or tungsten?
Both, because it is our UV visible DRS na. Here it is written there. See there. Both the lamps are present. UV lamp as well as visible lamp. And during the our characterization, what we are doing, we are taking the complete range 200 to 800, which is from UV to visible. Both the light source are present in that. We are using both the light source.
And we choose one lamp and switch.
We can do. Okay, that have also means for that we have option. Okay, so we are taking the complete range, sometimes 200 to 800 or 200 to 600. That the complete range is 200 to 800 nanometer. Okay, and based upon the observance of the sample, we will get a graph, and from that graph we can calculate, we can know what is the band gap of the material. And you know, as every means every person are not same. Similarly, every sample are not same. We will get different band gap for different samples. In some cases, we may get suppose 2.7 EV, 5 or 6 materials having same band gap, but that does not mean all the property of all the 6 or 2 3 samples are same. Band gap matches means that does not mean property will match. Okay, or have a doubt? I think Roshan have one doubt.
No, I don't have that.
I think you have one doubt.
I am just trying to visualize how this.
Okay.
So maybe that.
Move to next slide.
When to do the experiment.
Which one?
Means when we will do the experiment, maybe that will be more clarified.
Means you are thinking about instrumentation.
No. Means when we will do the.
Yes.
Using the.
You will get clear, means you will get during experiment, you will get much more knowledge, and at that time we can compare what we have studied there here and what we are doing there. It will help us at that time.
One more thing is that there is a signal IR, IZ. What is that? And just please explain that.
Which one?
IR and I naught. What is
It is your incident ray and reflected ray. I0 is incident, completely I0, reflected.
So it was like this, like.
A graph you can get. Okay, it is just for a sake of example. It is just we may not get the means same type of graph everywhere. This is here only for a sake of example, that we will get a graph. We will get a graph. Clear? Or in doubt?
No doubt.
Okay. Sorry, it is a blank slide. Anyway, Frank content principle. You know, in for liquid we studied that is what is that? Beers-Lambert law. For solid, it is very important like that. Okay.
For solid product.
Okay. Here, since electronic transition occurs very rapidly, you know, electronic transition occurs very rapidly. Definitely, it happens very rapidly. Transition means, you know, Jablonski diagram is there. You have some idea about that. Singlet state, triplet state, and the time span is very means very less. It is 10 to the minus 15 second. It femtosecond. Femtosecond. Right. Okay. So you just imagine 10 to the power means 10 to the 15 times smaller of 1 second. Okay. In that time range, transition occurs. Okay, that means it is very fast. Yes or no? It is very fast. Vibration and rotation of the molecule do not change the internuclear distance appreciably during the transition. What I have told you in the previous slide, that only electronic transition will occur, vibrational rotation will not occur. Okay. The intensity of transition is greatest for the largest of the vibrational wave function. In view of the Frank-Hunter principle, electron transition occur vertically on a potential energy diagram. You know, the transition will occur vertically in a potential energy diagram. Okay, means the transition, you know, in electronic transition, always which electron will get transmitted? Which electron? Outermost, valence electron. We cannot excite in UV visible region, we cannot excite 1s electron. We cannot excite 1s electron. If you will ask me, suppose if we will take hydrogen, but hydrogen is a gas, it is not solid. If we will take a hydrogen, then we can excite 1s electron, but condition is it should be solid. But hydrogen is a gas. So, it is only used for the excitation of valence electrons. Yes, yes, I have all told you that. X-ray. Yes, KSL, core electron. Okay, in XRD that have such much energy, sufficient energy that can eject from the electron from the cell which is near to the nucleus, but it have not such much energy. It will excite the electron from the valence cell.
That means in XRD, core electron will be excited.
Excited.
But in case of
Yes.
invisible, means in case of solid sample, only the outermost.
Only outer. If 2s is outer, the 2s electron will be excited. If 2p is outer, 2p, 3s, 3p, means only valence electron will be excited in this case. Only valence electron. And if the valence electron will be excited, it will move to the uppermost cell which contains almost no electron. And the person who have no friend, why it will stay there? It will again come back to its home, like that. You just think like that.
Okay, in case of the solid sample, like what you have excited from valence cell, outermost cell. In case of liquid sample, same.
No, that's why I have already told you that in liquid sample what we have to do, we can calculate concentration. In liquid sample we have not to measure the what is the band gap. In liquid sample we have to calculate the concentration. Nobody will ask you, I think, what on the basis of knowledge what I know till date, no one will ask you what is the band gap of a liquid sample, what is the band gap of water. It might be there, but I don't know. What I know I am telling you. If there is a solid sample, no one will ask there what is the concentration of solid sample. At that case, they will ask you what is the band gap of solid sample. Get it, na? In liquid sample, yes, observance. Okay, in liquid sample, someone will ask you what is the concentration. If 3 or 4 samples are there, which is more concentrated? By testing in UV-Vis DRS, you can tell it is more concentrated. But in solid sample, no one will ask you what is the concentration of the sample. They will ask you what is the band gap of the sample. Clear, na? Or have any doubt? Clear? No doubt? Okay. UV visible spectroscopy in photocatalysis. Okay. Till now, what we study about the UV visible spectroscopy. Then what is its application for us? Means in our field, it is also very important. That's why we are studying it. Yes or no? In photocatalysis. So before going to this one, first thing one should think what you should have know. What is photocatalysis? The catalysis which get activated in presence of photon. The catalyst, not catalyst, catalyst which get activated in presence of photon. What is the role of catalyst?
Enhances the reaction.
How?
By lowering the activation.
Right. By lowering the activation energy of the reactant. And photocatalysis get activated in presence of photon or interaction with photon and reduces the activation energy of the reactant.
We get photons from the sunlight.
any light source, whether it is sunlight or it is our light, any light, entire light source you can get it.
Okay. The intent, suppose we take any type of.
This type, actually what I am telling you, the light should be intense. Sunlight have more intense than this type of light. But if our catalyst is such much powerful that it can absorb this type of light, then it is possible. If we can prepare a light, a catalyst which is light sensitive, then it is possible. If you can prepare, means such type of tube light sensitive, how much intensity? It is very less intense. If it is not possible, for science everything is possible, you know. So if you can prepare, if you can develop a catalyst which is very sensitive to any type of light source, even it is least intense, it is possible. And our target is to prepare such type of material. Yes, light sensitive material, so that we can do any type of reaction in minimum cost. Then what is the difference between catalyst and photocatalyst? In catalyst we have to use heat, in photocatalyst free energy is there, na? Sunlight is there. Okay, now we will move to, okay, here the photocatalyst is a catalyst that changes the rate of a chemical reaction when comes into the contact with a source of light by absorbing light energy. The best example photocatalyst is photosynthesis. You know, we are getting all the knowledge from nature, then we are developing that in our laboratory, because we cannot prepare 100% natural things. We cannot develop 100% natural things. It is quite, I am not telling it is impossible, but it is very difficult to prepare a 100% natural thing in lab, right now. These are some examples: ZNO, ZNS, CDS. Okay, I have told you what is the difference between metal, semiconductor, non-metal. In the that, so here I am explaining about only semiconductor. Not I will not go for sorry, metal and non-metal. These all are semiconductors. Okay, MOF is metal organic framework and COF is cobalt organic framework. UV visual DRS used to calculate the band gap of a photocatalytic material by using the equation. This is the equation. I will tell you and explain you in later slides. Okay, next slides I will explain that one. How can you calculate the band gap by using this equation? Clear? Or have any doubt? Okay. Now come to, this is the basics. Yes, yes, yes. Which one? I will tell you. Yes. From this we can calculate whether it is UV range or visible range. I will tell you that one. Okay. So this is the basic. Okay. First I will start from this one. Why visible light is very important for us? You know, in sunlight only 3% is UV. Okay. Only 3%. It might be 3 to 5%. Okay. Visible is 42%. Not exactly from 42 to 50 or 45, but 42%. Here I have given it. Infrared is rest 58%. Okay. So if we will develop a UV material, it can absorb only 5% light, and if we develop a visible light type of material, it can absorb 42%, and if you can develop a infrared type of material that can absorb the infrared ray, it can develop 55%. Okay. And till that the scientists are doing research in that field to make highly efficient to the materials. They are trying to change the materials from UV to visible. Then after, the research is going on to develop the quality of the material as well as to improve.
That is, that if they are trying to make IRP materials.
They are trying, yes. If it is possible, then they will do this. If we can develop a material which is 100% IR active, then what will happen? This light is also not required for us, because this is UV visible light here, right? That is present in IR, means the material which is IR active. UV visible light is also not UV visible light is not important at that condition. The reaction can also happen in the dark, because IR ray, you know, yes, we are able to see only visible type of light, na? to which we are not able to see, that is dark. What we are telling? The things to which we are not able to see, we are telling that dark. That means IR is not present there, IR is present there, but we are not able to see that. Yes or no? 50 to 60, you just okay. अधिक अच्छी हाँ. Research is going on to get the, it is not what we are telling, it is very easy, but to get that it is not such much easy what we are telling. The research is going on.
Radiation is that much efficient to cause the electron transition, electron transition.
IR radiation,
Is that much efficient to cause?
you just think one thing, okay, the UV to visible is 200 to 800 nanometer, okay, 200 to 800 nanometer. In our some of our material that we have developed, we just get the band gap that is very less, okay, okay. We have some material very means maximum 1 to 2 material, some of in a lab which are IR active, not 100%, okay. Clear? Can you move to next one? Yes. Okay, yes, this one. So it is all so that we are trying, suppose if we have developed a UV material, suppose a white material, then what we have to do? We are doing various type of experiments, means we are just adding some what, suppose black, any type of different type of semiconductor. In that case, that is doping, heterojunction formation, co-catalyst loading. These are some crystal engineering by which we can reduce the overall band gap. We cannot reduce the band gap of the material, we can reduce the overall band gap of the composite. Okay. By that case, we can do active the material, we can call the material if whether it is UV active or not. And yes.
Okay. No, the gap is clear, but this one.
I am telling this one, okay. You know, this is a light source. It is actually sun, means it is not exactly visible light source, it is sun light source, okay. So it is your suppose catalyst. When light strikes here, the electrons are present here, the valence shell. This one is the valence shell. This one is the imaginary state up to which the electron can move. Up to which the electron can move.
That is conduction band.
Conduction band. You know, if we will throw a ball with with different force, the ball will touch some different height, like that. Different metal have different light absorption capacity. On the basis of that, the electron jumps, means the conduction band will be different.
So the conduction band is not fixed.
It is not fixed. It is imaginary state. It is imaginary state. Up to which the electron will move. Up to which the electron will move and touch that point and again come back. And between this period, means this electron moves to the conduction band and return back, we have to use that electron, otherwise it will again come back here. Recombination will occur.
Okay. That means in between valence band.
Before electron reach at the valence band, we have to use the electron. Two forms. It may be dissipate in the form of light, it may be dissipate in the form of energy or heat. When the electron returns back, it loses energy. That loss of energy, that might be in the form of heat or it might be in the form of light.
Why we are not using sunlight?
Why?
We are not using sunlight.
Where?
Instead of using
Here we are using sunlight.
direct sunlight.
Yes, we are using direct sunlight. Okay. So
Which condition would be better when electron get excited to conduction band? So before it coming back to the
yes, I have told you na, we are doing crystal engineering, we are doing some, suppose if we will attach another semiconductor here, thus so that this electron will jump to that electron, that state. Okay. So, at that case it will not, means there is a minimal condition to return back this one. Clear?
That means component formation.
Yes, composite formation or co-catalyst loading or heterojunction formation. By that means we can increase the lifetime of electron as well as hole. If electron moves from this one, here creates a hole. We can use both electron and hole, because hole, if hole is there, it can trap the electron from any other reacting material. If electron is there, it can move to any other. You just see here, if electron is there, it can use convert oxygen to superoxide radical, and if a hole is there, it can convert OH minus hydroxide radical to hydroxide ion to hydroxide radical, because if ion is there, two electrons is there, it will trap one electron. So, now it is OH dot. Now, these two are very active species, and these two will proceed the reaction. Clear? Or have another doubt? Clear?
So, actually, just I get confused because this how water get into radicals into OH radical and O2, and how this.
No, it is a very general sense. It is possible.
Means how? Means I understood what.
Suppose this, it is a superoxide radical, right? It is a superoxide radical O2 dot. So, it is here water is present, which contains H and OH. Now, it will, you know, if H and OH are there, if H, okay, whiteboard is okay. If H and OH is there, it will break into two radical form, H dot and OH dot. So, now this O dot will bonded with H dot to form HO2. If we will bonded with 2 water, it will form H2O2. If we will, this O2 will combine with 2 water molecule, 2 H radical, it will form hydrogen peroxide and 2 hydroxide radical. Yes or no?
Initially oxygen is there, then when we are excited,
Yes.
then it.
First case is oxygen will be reduced to form superoxide radical.
Okay. Then in this case, in the bottom case,
Yes.
OH radical converted.
No, it is not, it is hydroxide ion, OH minus. In water, that is OH minus is there, na?
OH hydroxide.
And OH minus is OH 1 minus means 2 electron. So, this hole can trap 1 electron. The remaining radical is there, OH radical, and radicals are very active, reactive in comparison to ions. We know. So, that these will further what? Do the reaction, if means the reaction, we are supposed to do that.
Okay. That oxygen converted to oxygen radical.
Yes.
Where the oxygen came from?
In the reaction medium?
Okay. And hydroxide ion from the water.
Yeah, water. Okay. Or have any doubt? Any doubt? Clear?
That was MB or BB mineral.
Which one? It is one type of our pollutant. Okay. Methylene blue, dye. Okay, dye. So, clear? This is a photocatalysis. Why we are trying to do our material more visible active? This is the reason, because visible light is more active. Okay, and this is our different types of materials. Different types of materials having different band gap. Clear? Next slide.
What says NHE?
I will tell you. Okay. NHE, SHE, what I will tell you. Okay. Actually, you know what is in electrochemistry? We just calculate the band gap. Means from the UV visible spectroscopy and Morse-Schottky diagram. From Morse-Schottky diagram, we can get the flat band potential.
Which potential?
Flat band. Okay. And there is equation at which we have to put that value. After putting that value, I will get the, from UV visual DRS, I can get the band gap. But to get this, what is the value of VB, what is the value of CB, So, for that case I have to do electrochemical Morse-Schottky analysis. So, in that case NHE and RH will come or SHE will come. Yes. Not only from Morse-Schottky, from Morse-Schottky and UV visible DRS. From UV visible DRS we can, I will explain that later. Okay, you just wait for one. No, only gap we can know, as well as VBCB also we can know, but in addition to Morse-Schottky analysis data. I will tell you that. Anyone, if you will get anyone, then we can get another one, because band gap is known. If we will get VB, we can get CB. Okay, I will explain that one. Okay, next. Here. Clear? Or have any doubt? So, UV visible, okay, I have already told you. The next thing is, what is important thing is in this, it is one is direct band gap, one is indirect band gap. Okay. So, one question might arise on your mind that what is direct and what is indirect. Okay, I will explain that one. Okay. So, you first, I have already told you this one. How can you calculate the band gap, right? And after getting band gap, you know what you have to do. There is a formula. I will tell you that later. By putting that one, we can get the direct band gap and indirect band gap. Direct band gap and indirect band gap. I have not given here all these things there, because that will be very broad. Means if I will add that here, that will be very broad. Okay, but I will explain that everything here. Okay.
Just tell us that what is the use of direct band gap and indirect band gap.
Yes, I am telling. You know, this electron moves from this one and returns this here. This is direct. This electron comes here, then returns here. It is indirect. You just go to the Jablonski diagram. You just go to the Jablonski diagram. Singlet state, triplet state, you know. Not exactly. Recombination rate, we cannot assume that by indirect transition the recombination will be reduced. Okay. But which transition it follows, we can get from. No. What I know, I am telling that one. There is no such advantages between such direct or indirect. Okay.
Indirect, the electron goes from where to where?
I am telling that one. You know, first thing is, I have told you it is your valence band. First, electron will be excited from valence band to conduction band. Okay. Suppose you know K cell, L cell, M cell, N cell, O cell, like that. Then what cells are there? Okay. Suppose such electron have gained such much energy that will be go from our M cell to O cell and return back. Got it? Direct. Okay. Suppose the electron got some energy, but it is unable to move from that state to directly P state, means our KLMN, NOP. Suppose it is unable to go to P state, but it moves to O state, then return back by getting such much energy. At that case, we just assume whether direct band gap or indirect band gap occurs. One more thing is there. In direct band gap, electrons and photons are interacting. Photon, electron, right? In fluorescence, phosphorescence is completely different. Such type of mechanism. Okay, but in our indirect band gap, electron, photon, and another term is phonon. Okay, you can get it. It is very fundamental thing. You just keep it in mind. You may get such type of question in interview, but you have not to tell anything else except this thing. That direct band gap, only two things interacts, electron and photon. In indirect band gap, three things interact, electron, photon and phonon. That's it. Nothing else. You have not tell anything else, because this direct and indirect band gap is a very vast thing in physics. It is not a small thing. It is a very vast thing. In physics, it is a very vast thing. There is a very long calculation is there to know. No. We can get that from the calculation, whether direct or indirect. Okay. So one thing you keep in mind, in direct band gap, keep in mind, is very important question. You may get this question in any type of interview. What is the difference between direct and indirect? You must have to tell two things are interact in direct: photon, electron. Indirect, photon, electron and phonon. That's it. You can get it in Google. You just check that. What is phonon? Okay. Okay. Then what is the difference between direct band gap and indirect band gap? It is all about. Okay. So that, but in latter case we will get the whether the material moves means shows direct band gap or indirect band gap. I will show you example here. I will tell you. You just wait for 1 minute. When I will go to the slide, I will tell you. Okay. So, in this slide, one thing you have to know: direct band gap and indirect band gap. It is very important one. And actually, it is quite difficult to explain this in these two sentences. It is a very big thing. Here, electrons and photons interact. Electron, photon, and phonon interact. This is the only one and correct answer. Except there is some other answer there, but this is very important answer. Okay, here I have given an example, right? You just see here. Here I have given an example, right? You know, x-axis wavelength and y-axis observance. Okay, here I have shown here some examples. You know, this black is your UV-Vis 60NH2. It is a one type material. I just loaded gold, then palladium, then gold palladium mixture 1:1, 1:2:1 in different ratio. Yes, these are co-catalyst. Okay. Then what I get here, you just see here, you know, this type of some peaks are arises here. Okay, and it will show some different band gap. It will show some different band gap. And the here, you know, the band gap I found 2.67 for the metal NH2, and for the rest of thing I have not calculated here. Okay, so such type of graph we will get from UV visual DRS. Such type of graph, not that type of Z, not that type of graph. If you will get that type of graph, then you should be sure that your sample is not right sample. 100%. I will tell you. I will tell that one. Yes. What is red shift, what is hypsochromic, bathochromic, hypo, I will tell you that one. Okay, you just wait. So, okay, it is our indirect band gap. You know, here 1/2 is there, na? Here alpha h nu 1/2, it matches with indirect band gap. It shows indirect band gap, not direct. If it is, it will be whole means 2, then it will be tau plot, TAUC. Okay, clear? This is UV. From UV, we have to put two formula for direct band gap, for the indirect band gap. Okay. Suppose I will tell you how can we calculate, how just we get to know which one is perfect for our result, direct or indirect. I will tell you that one. You just wait for that. Clear? Clear?
What is that LSPR?
It is LS actually for noble metals like gold, palladium, you will get localized surface plasmon resonance. For the timing, it is not important for us. We will discuss it later. Okay. It is a property of noble metals like gold. Okay. So you know what we are asking about: bathochromic shift, hypsochromic shift, and here hypochromic shift and hypochromic shift. Okay. We just move to previous slide. We just see here. This was the peak of parent material, black one, and in composite formation we get peaks lower. Now you tell me which type of shift we get here? Hypochromic shift. Okay, and here I have given an example. It is black one, PPO. After addition some materials with PPO, this peaks moves in right direction. That means bathochromic shift or red shift. Yes. I am explaining that one.
Recombination.
Not recombination, whether it is UV active or visible active, that is very easy. I will tell you. Actually, we have to draw a tangent here, and at which point it intersect, we have to divide that with that the previous formula. You know, here we have to divide it here, lambda value. After getting that interaction point, the value we have to put here. If we will get by dividing with 1240 38, if we will get the value below 2.7, then we call it as visible active. If we will call it as what? If we just get the value more than 3, we call it as UV active material. Clear? Which one? Here, peak position. Actually, I am explaining that one. Okay, you know, in some cases you will get very sharp peak, intense peak. We call that intense peak. In some cases, we will get less intense peak. If a material is clear, we will get intense peak. After gold palladium loading, the material get rough. The material get rough. Okay, so in that case, it might not be possible to get the very sharp peak. Clear or not? बुझीपाल नहीं मुझे कहली जितेबाला आमर गोटे मटेरियल अच्छी मटेरियल जी आसूँ बैंड गैप मतलब हाइट जी आस पीक हाइट इफ विल add some material with it. Okay, now the surface of material, suppose this is a surface, I add this one. So the graph I have got previously, I will not get the same graph here. It might increase or might decrease. If it is means arranged in a sequence, the peak height may increase. If it arranged arbitrarily, at that case peak may be means we may get less intense peak. If our yes, like that. If our arrangement is very sequential, we will may get high peak, or else we will get less intense peak. Clear? Or have any other doubt? How many time is there?
It's already 6:40.
Okay, 10 minutes more. Okay. Okay, this part is over. Okay, it is band gap calculation. Okay, there are two types of formula. First is this one, EVB x minus EE plus 0.5 EG. Okay, here EE is constant 4.5. Okay, and x is absolute electronegativity value. Okay, by putting and this we have to calculate what is the absolute electronegativity value of a material, because you know this one is constant. So we have EG we can get from band gap, UV band gap we can get that by dividing with 1240. So we can get EVB and ECB equal to VB minus BG, EV minus band gap. We can get, okay, for polycrystalline material, for polymeric material, this formula is not applicable. Polymeric, because you know in polymer there is much more compounds are there. So at that case we cannot calculate the electronegativity material. Suppose if we have only zinc oxide, we know what is the value of electronegativity value of zinc, what is the value of oxide, we know. If I will take ethylene, yes, that is not sum, that is average value. Yes. Okay, if I will take ethylene, I don't know how much molecules of ethane is there in polymeric compound. So at that case we cannot calculate what is the electronegativity value. Clear? At that case we have to calculate, we have to depends upon the which one? Morse-Schottky analysis. At that case we have to depend upon electrochemical Morse-Schottky analysis, and from Morse-Schottky analysis we can get EG, AG cell value and pH of the electrolyte, at which pH we just run the reaction, and we can get here EVB or ECB. After that we can get the band gas. Yes. No, not exactly. That have two types of calculation. Here I have put pH 7. If we will calculate at pH 7, we can get band gap. If we will not take any pH, then we will get the pH at which we have carried the reaction. Okay. So
We are having a silver electrode.
yes, AgCl electrode and platinum electrode.
Okay. That's why we are fixing this.
We have a 3 electrode system. AgCl,
In our lab.
yes, AgCl, platinum, working electrode.
Working electrode.
Working electrode means the sample to which means on which electrode we take our sample, that is working electrode. One is reference electrode, one is counter electrode. Yes, band gap. In this case we can get EVB. Similarly, in this case we can get either EVB or ECB. There is two type of material, P type and N type. For different material we will get either EVB or ECB. If you just know one thing, from this equation I will get one thing, either EVB or ECB. If I will get ECB and band gap is known, that depends on P and N type material. P type material, you know what is P type material, what is N type material? No idea. What is P type and N type material? Yes, holes are major charge carrier. N type materials are electrons are major charge carrier. Yes. You may get positive or negative. If you will get positive, you have to minus it from this one. If you will get negative value, you have to put the same formula. From Morse-code analysis, you will get different type of graph. If the graph is like this, it is N type. If the graph is like this, it is P type. If the graph is like this, it is P and N type. That is electrochemical study. Yes. From Morse-code analysis, you can get whether it is P type or N type. Okay. So, if the graph is like this, it is N type material. If it is like this, it is P type material, P N type material. Yes. Okay. Ansumika, late hochi. 5 minutes more. Sorry. Sorry. Pratiksha, I am sorry. Okay. I will finish it within 5 minutes. Number of slides are there, but she is being late. Huh? Okay. You know, here direct and indirect band, you know one thing. It's okay, 5 minutes more, I will finish it, I will complete. Okay. So, this one was actually very important, because it is means we have to follow this to calculate the band gap. We will discuss it later, not now, because you are in late now. Okay. How to calculate direct and indirect band gap. This is the actually this slide is very important. Among all this one, that was the fundamental. This is the practical part to which we will do apply. Okay. So, this is the formula by which we will tell you it later how to do calculate band gap, and it is your direct band gap and indirect band gap. Okay. Division indirect band gap, it is your band gap. Okay. We will explain it later. So, practical example, there is example, but I will not given right now because you are in late. So, we just leave it. Okay, over. Yes, finished. Actually, I have put 2 examples for your clearance, means to get clear understand. I just want to draw there, but she is in late now, so we will finish the class here. Okay. Later we will discuss that how to calculate band gap, how to calculate direct band gap, how to calculate indirect band gap, and which one is more nearer, means accurate for our band gap, means whether direct or indirect. Okay. Will, if possible, I will take a class for PL na. At that case I will tell you how photoluminescence. ସେଥିରୁ ଆମେ ଜାଣିବା କାହାର ମାନେ କୋଉଟା ମାନେ କ'ଣ ଆମେ ଧର 3 to 4 ମେଟେରିଆଲ ନେଉଛୁ, କେଉଁ ମେଟେରିଆଲର ରିକମ୍ବିନେସନ୍ ଟାଇମ୍ କମ୍ ରହୁଛି, ବିକଜ ରିକମ୍ବିନେସନ୍ ରେଟ୍ ଓଭର ଆମର ରିଆକ୍ସନ୍ ଡିପେଣ୍ଡ କରୁଛି. ସୋ ଆଟ୍ ଦ୍ୟାଟ୍ କେସ୍ in that class I will explain how to calculate band gap, indirect, direct. No, so I will finish it. If you have any doubt, you can ask, because this is the only class for your UV visible. Later we will discuss, but if you have any doubt, you can ask. Sorry, Pratiksha, you are in late.
Today that uncompleted part, please.
We will discuss that. That last slide was the only important slide for today. Okay, because here I will means I am supposed to tell you how to calculate by taking one example. I want to tell you how to calculate band gap, how to direct band gap, how to indirect band gap, and which one is more right for a particular case. But for today I will stop here. In PL class I will take these 2 slides again, then I will take PL class, right? Thank you. Definitely, definitely. Okay, clear, over.